First stop, the place physics went to break. Black holes. The black hole's secret hard drive. Emotional setup. Pride, risk, and a rule that refuses to break. Payoff. A surface ledger that saves unitarity and your data. The stakes landed like a gavel in the 1970s. Jacob Bekenstein noticed something no one expected. When you drop stuff into a black hole, its surface area grows in lockstep with the amount of disorder you feed it. He dared to call that area an entropy, information content, measured in square Planck lengths. Not the volume inside, but the boundary. That was the first unsettling whisper. The bookkeeping sits on the skin. Then Stephen Hawking ran the numbers that stunned everyone. Quantum fields near the event horizon churn out radiation. A black hole glows, bleeds mass, and evaporates. Purely thermally, he said. Featureless. Like steam carrying no details of the teapot. If that's true, all the microscopic structure of what fell in, books, stars, your playlist, burns away. The information paradox was born. Either quantum mechanics' unitarity fails, or Hawking's horizon isn't telling the full story. Here's where the chalk dust thickened. Leonard Susskind and Gerard Hooft wouldn't yield unitarity. They trusted the rules of quantum mechanics. Information evolves, it doesn't vanish. So they aimed their fire at the horizon. What nobody knew at the time was how far the argument would reach. Susskind's answer leaned into Bekenstein's area law. If black holes radiate, then the information must ride out, somehow encoded in subtle correlations in that radiation. The horizon becomes a storage device, a 2D ledger for 3D events. Human moment. The black hole war wasn't just physics. It was pride, persistence, and reputations on the line. They bet physics on a chalkboard war. Hawking, brilliant and blunt, wrote thermal spectra. Susskind, relentless, sharpened the idea of holography. The outcome wouldn't be settled by rhetoric, but by a theory coherent enough to save unitarity without burning the horizon. No joke, careers hung on this. But there was one problem. Hawking's calculations seemed too clean. If the radiation is perfectly thermal, there are no signatures to decode. You can't reconstruct a manuscript from a fog bank. So either the radiation isn't perfectly thermal, or the horizon isn't a featureless membrane. Meanwhile, something else was happening. String theory, playing with extended objects and dualities, started to hint that counting microstates of certain black holes matched Bekenstein, Hawking entropy exactly. The number of ways the hole could be.
Built, microscopically, scaled with area. That's the sort of receipt theorists live for. This was the moment everything changed. While Maldacena proposed a precise duality, a gravity theory in a bulk space-time could be exactly equivalent to a quantum field theory on its boundary. In that world, a black hole in the bulk is described by a hot state in the boundary theory. The information is never lost because the boundary theory is unitary by construction. The paradox doesn't vanish, it dissolves into a dictionary. Bulk geometry and boundary entanglement are two languages saying the same thing. If you can translate, you can keep track. Impact came fast. If area governs entropy, then the maximum information in any region scales with its surface. The holographic suspicion wasn't a metaphor anymore, it looked like a rule. Physics inside a bounded region is fully captured by physics at the boundary. Black holes weren't trash cans, they were vault doors. The event horizon, once a one-way ticket, started to look like a billboard of bits. Complications didn't stop. The firewall debate hit like a siren. To keep information in unitarity, some argued the horizon couldn't stay smooth. A would-be traveler would hit high-energy quanta, fire, challenging the equivalence principle that says free fall feels locally calm. Others proposed that quantum entanglement and subtle non-locality rescue the horizon without torching it. The community split over where to place the weirdness. At the horizon, in non-local correlations, or in our assumptions. Meanwhile, new tools tightened the ledger. The Hayden-Preskill thought experiment recast black holes as fast scramblers, systems that quickly smear information across their degrees of freedom. Throw in a qubit, wait a scrambling time. In principle, the outgoing radiation begins to reveal it. And years later, calculations of the page curve, how entropy of radiation should rise, peak, then fall if information returns, were reproduced using new semi-classical techniques with islands that effectively let the boundary do the bookkeeping. The ledger balanced. The receipt existed, even if it was weird looking. Human beat. Picture Hawking, late in life, conceding a bet about the fate of information. The chalkboard war didn't end with humiliation. It ended with clarity earned at the cost of ego.
Physics moved on, scarred and wiser. Stakes, again, right now. If the deepest information budgets live on surfaces, then 3D is a story told by a 2D account. Not fake, re-encoded. Your memories, your choices, the heat in your face after a run, the way a song raises goosebumps. If information is conserved, they don't burn, they migrate. The black hole's secret hard drive is the horizon. The bits aren't little squares, they're quantum degrees of freedom, bounded by area, like breath fogging a cold window that still remembers your outline. And if that's how nature stores the most extreme data, what about the rest of the universe? Does space-time itself get its instructions from an edge we don't see? And that still writes you down? One detail will prove crucial later. The size of a bit in this bookkeeping naturally points to Planck scale areas. Not a lattice in space, but a limit on how much can be packed into a patch. If the universe hides information on surfaces, what's the size of a bit? To answer that, we need to talk about the smallest meaningful scales. The place where trying to zoom further only blurs the image and bends the rules. The universe's pixel limit, Planck scales, emotional setup, curiosity versus frustration. Payoff, a hard ceiling on detail that reshapes what place means. To understand the size of a bit, we go to the edge of meaning. There's a scale where our equations start arguing with each other. Push quantum mechanics to measure positions with absurd precision and gravity pushes back. That standoff defines the Planck scales, a length around 1.6 times 10 to the minus 35 meters, and a time around 5.4 times 10 to the minus 44 seconds. Below those, not much is promised. It's not a brick wall, it's a warning label. Stakes first. If there's a minimum, meaningful patch of information, an effective pixel, then the smooth 3D we trust might be a smart rendering, not an infinitely detailed map. That matters because everything we think we know about locality, causality, even what counts as a place, depends on the idea that you can always zoom in without changing the rules. If space has a resolution limit, high-frequency modes of quantum fields can't be counted freely. Infinity, the old friend of field theory, gets means tested. What actually happens when you try to zoom? Start with a simple plan. You want to localize a particle to a tiny region. Heisenberg says the more precisely you pin down position, the more momentum uncertainty you pay. Big momentum means big energy. Cram enough energy into a small enough volume, and general relativity adds a new twist. You bend space-time. Keep going, and
you cross a threshold. The energy you needed to resolve the spot makes a horizon around it. Your microscope becomes a black hole. The act of measuring builds a curtain. That mashup of quantum fuzz and gravitational collapse defines the intuition behind the Planck length. It's the scale where our two best theories refuse to be used independently. Not because nature is coy, but because our tools aren't built to be used there without a unified manual. The takeaway, past that point, the question where exactly stops being well posed. The pixel limit isn't a grid on space. It's a cap on information density in a region. Let's talk energy density. If you tried to pack one quanta into every smaller and smaller wavelength mode, field theory hands you ultraviolet catastrophes. Gravity fixes the accounting. The Bekenstein bound tells you, for a given area, you can't store unlimited bits. Entropy scales with area, not volume. So any model of fundamental stuff that pretends you can count modes down to arbitrarily tiny lengths without consequence is missing a line item, the cost of curvature. We need metaphors without traps. Minecraft suggests cubes. That's not right. A better way. Think resolution versus rendering. Your monitor has pixels, but your eyes feel smooth gradients, the glow of a sunset leaking from orange to violet, because anti-aliasing and interpolation soften the edges. Holography is closer to that kind of efficiency. The world isn't tiled in squares. The world obeys an information budget that caps the number of independent degrees of freedom per surface area. The geometry you walk through, the way your knuckles brush a doorframe, can feel seamless because the encoding is redundant, error-corrected, and highly correlated, like a high bitrate stream that never buffers, even when the bandwidth is finite. Here's where UV cutoff language gets slippery. Many theories regularize infinities with an artificial grid to make calculations behave. That's a mathematical scaffold, not evidence of literal space-time pixels. The Planck scale is different. It's a physical hint that gravity itself becomes part of the micro-local story. High-frequency modes don't just get cut off, they back-react. They change the stage you're trying to measure. So when we say pixel limit, we mean an effective limit on independent,
locally accessible information, not a cosmic checkerboard. Microstory. A graduate student tries to zoom past Planck with higher energy probes to sharpen a position measurement. The equations spit out a horizon radius bigger than the target region. Her advisor smiles. She's asked her toaster for WeF5. It's not that the toast is lying, it's that she used the wrong interface for the job. Honestly, that's my brain every Monday before coffee. Meanwhile, something else is happening in the math. In theories with gravity, attempts to boost resolution translate into increased entanglement across boundaries. That entanglement, those correlations, want to grow with area. The Ryu Takayanagi idea we'll get to later makes that precise in special spacetimes. The area of a minimal surface computes entanglement entropy. Translation: the more you try to distinguish interior details, the more the boundary must carry. So does a smallest length mean causality breaks? No, it means operational definitions change. You can't perform experiments that cleanly access distances below a certain scale without triggering new physics you can't ignore. Local quantum field theory is a fantastic approximation all the way down until gravity insists on a seat at the table. Past that, locality may be emergent, the way sound waves in a crystal are emergent, real, measurable, but not fundamental. This is where holography below Minecraft needs repeating. The intuition of pixels helps us think about budgets, not bricks. A Planck area patch is better thought of as 1 qubit's worth of capacity in an optimal code, not a tiny square that sits somewhere in space. Different theories propose different microarchitectures for those qubits, string bits, spin networks, boundary conformal degrees of freedom, but the limit they respect is shared. Area bounds set the bill. What would we expect to see then? If a resolution limit exists, extremely high frequency fluctuations should be suppressed or reorganized by gravity's rules. Correlations at the smallest scales might be less independent than naive field theory predicts. In cosmology, that could shave power off certain modes or shape how primordial fluctuations entangled across horizons. In the lab, interferometers chasing Planck-scale noise look for correlated jitter that can't be blamed on ordinary quantum vacuum fluctuations. We'll go there soon. One more caution. The Planck scale is not an invitation to declare discreteness everywhere. It's a clue about information and dynamics. Some approaches, like loop quantum gravity, take it as evidence for granular spectra of area and volume. Others, like string theory,
soften interactions with extended objects. Different roads, same signpost. At tiny scales, the channel capacity of space-time changes. So what's the size of a bit? The bookkeeping points to the Planck area as a natural unit. But the bit isn't sitting inside the bulk like a pixel in a photo. It lives in how boundary degrees of freedom can encode bulk possibilities without violating gravitational back reaction. We've met the limit. Next question. Where's the universe's screen hiding? Where's the screen? Boundaries that store reality. Emotional setup. Disorientation that turns into relief. Payoff. A working dictionary that makes erasure illegal. If the universe keeps its books on surfaces, we need to find the surface. The clue came from an unlikely place. A space-time with negative curvature, anti-de Sitter space. It's not our cosmos, but it's a clean sandbox with an edge that behaves like a stage. In 1997, Juan Maldacena wrote down a daring equivalence. A gravity theory in the ad-is bulk is exactly the same as a quantum field theory living on its boundary. No almost. A dictionary, line for line. Stakes first. If this duality is right, then geometry, distances, black holes, even the passage of time inside the bulk, maps to patterns of entanglement and dynamics on the boundary. That means space can be reinterpreted as a story told by correlations. What we call inside is re-encoded outside. If a black hole swallows a diary in the bulk, the boundary theory never loses the plot. Its quantum state evolves unitarily. Information isn't destroyed, it's translated. Action. In ADS CFT, every bulk field has a partner operator on the boundary. A ripple of a field deep inside corresponds to a specific tweak of the boundary state. Thermal states on the boundary look like black holes in the bulk. Hawking quanta, radiating outward, show up as ordinary excitations in a perfectly unitary quantum theory. The paradox that tore the community for decades becomes bookkeeping. If you can read the boundary, you can reconstruct what the bulk did, at least in principle, and in regimes where the dictionary is usable.
Here's the human beat. Maldacina's paper landed like a quiet bomb. Offices went silent, then hallways filled. People who'd been arguing about horizons started arguing about correlators, conformal symmetry, and how to invert the map. The shock wasn't just that a duality existed, it was that it was exact enough to compute with. A whole generation recalibrated their intuition. Gravity might not be fundamental, just the emergent language of entanglement woven across a boundary. Impact. The duality sparked a second revelation. Maybe geometry isn't a backdrop. It's braided from entanglement. The more two regions of the boundary are entangled, the more securely stitched together the corresponding patch of the bulk becomes. Cut the entanglement and the bulk can literally pinch apart. This sharpened with the 2006 to 2007 Ryu Takayanagi proposal. The entanglement entropy of a boundary region equals the area of a minimal bulk surface that hangs from that region's edges in Planck units. Area equals entanglement. Bekenstein's whisper turned into a working tool. Meanwhile, something else was happening. Tensor network toy models like Mera and Happy Codes drew pictures where quantum states are built by layering entangling gates that look like a discrete hyperbolic geometry. Errors in the bulk, local disturbances, could be corrected by reading multiple overlapping patches of the boundary. That's quantum error correction, not poetry. The bulk boundary map acts like a code. It's why the interior can be robust even if parts of the boundary are noisy. Space-time as a lossless zip file wasn't just a joke, it was a blueprint. But there was one problem. Our universe isn't ad-es. It's closer to de Sitter, with a small positive cosmological constant and no clean time-like boundary to hang equations on. The ad-es box has walls, our sky doesn't. So ad-es CFT isn't a copy-paste for cosmology. Attempts at DS holography exist. DS CFT, horizon holography, but none have the crisp, calculable grip that ad-es enjoys. The clue stands, the translation to our world remains unfinished. Still, hence multiply. Black hole microstate counts in string theory match area laws. Page curve calculations using islands combine semi-classical gravity and entanglement to reproduce unitary evaporation. And in condensed matter, holographic tricks help model strongly coupled systems we couldn't touch with perturbation theory. The dictionary isn't confined to the heavens. It speaks in lab materials and weird metals. So where would the screen be if not at infinity? For ad-es, the boundary is spatial infinity with time-like character. For cosmology, candidates include null surfaces like horizons, cosmological horizons, Rindler wedges, even the past light cone of an observer. Imagine it like this. Your life is lit by a lamp you never see, and the wall behind you, curved and unimaginably far, catches the
shadow of everything you do. The spirit of the principle says, pick a boundary that captures causal influence. Then count what can be encoded there. The area tells you the budget. The details of the code tell you how the interior shows up, like an MRI reconstructing a body from slices you never feel. Let's get precise about fingerprints. If bulk geometry is built from boundary entanglement, then changing entanglement changes geometry. In practice, that means mutual information and correlation structures on a putative boundary constrain what the interior can look like. Move the sliders on entanglement, and you warp distances. That's not a slogan, it's a set of formulas in ad-es you can compute. Even when we can't apply them directly to our sky, the pattern of logic survives. Information first, geometry second, complication. The cosmological constant problem looms. Why is our curvature so small and positive? What's the right boundary for a universe that keeps expanding? Without a sharp edge, holography feels like trying to hang a painting in a room with no walls. Some proposals anchor to the future boundary, others to horizons tied to specific observers. None are definitive. This is where humility returns. The mechanism looks right, the venue is still under construction. Human beat again. Maldacena smiles in talks when he says, "We don't live in ad-es," then keeps going. The point isn't to pretend we do, it's to learn how a universe can be both gravitational inside and quantum on a boundary. The experiment is the theory itself. Can this dictionary grow beyond its first language? Here's the transition we need. If there's a screen, it should leave fingerprints in the static. Not a logo, not a grid, constraints. Information bounds that shape correlation patterns in the oldest light we can see.